Hello everyone, and welcome back to our discussion of cup anemometers. And in this video we're going to talk about dynamic performance of a cup anemometer. So one dynamic performance characteristic is the distance constant, and it's somewhat similar to a time constant. We looked at time constants when we talked about thermometers. Now we're talking about anemometers, and we use something else called distance constant. And the distance constant is how much air needs to flow past an anemometer, a cup anemometer, to cause it to respond to within 63.2% of the increasing step function change in the speed. So in other words, the cup is spinning, the wind increases or decreases, a step increase or a step decrease, and how much more air needs to flow by the cup, the distance, for it to respond to that change, 63.2% of that change. I know it's kind of complicated, but we'll work our way through this. The equation that we use to determine the distance or time constant is similar to one that we used for thermometers, except now instead of T for temperature, we have V for velocity. We have tau. Tau is a time constant, and these V's are the initial is the wind speed, and then the also input wind speed, VI. So similar to our time constant for thermometers, here is an equation for the velocity of a cup anemometer. And you can see that the equation for any given linear wind speed, if you want to figure out a linear wind speed at any particular time, you need to know the initial speed of the rotating cup. Also, there's a constant K. U naught is the wind speed. In this case, V is the cup speed, but V naught is the wind speed. Or delta, I should say, U naught is the wind speed, and then delta U is the change in the wind speed. And then tau is your time constant, and T is time. So the linear speed of the rotating cup depends, of course, on its initial speed and also the initial velocity of the wind and how much the wind changes, and then also the time constant. All confusing, huh? So likewise with the time constant for thermometers, we can come up with the physical requirements for time constant for the cup anemometer. And in this case, it depends upon the characteristics of the anemometer. We're talking about a cup anemometer, so of course, you've got the coefficient of drag, you've got the area of the cup, you've got the cup wheel radius, in other words, from the center of the anemometer out to the cup. How far is that? That's the cup wheel radius. The density of the air is also important, as is the inertia of the wheel. Of course, the wheel in motion remains in motion, a wheel at rest remains at rest, so the inertia of that cup wheel. And then also the input wind speed. What is the input wind speed? So we can figure out what the distance constant is based on the time constant. So in our equation at time constant, you know that the velocity is equal to distance over time, so we're going to use that equation to figure out the distance constant. So in this case, the distance constant would be the input wind speed, or wind velocity, wind speed, times the time constant. Time constant is in seconds. Input wind speed is meters per second, so you end up with meters for your distance constant. Now, the tricky thing, though, is that the distance constant is constant, but the time constant is not. So by definition, we said that the distance constant is how far the wind speed or the wind has to travel past a cup to bring it to within 63.2% of the final value, or register 63.2% of change, I guess. But the time constant is a function also of the velocity of the input. If you have a faster wind speed initially, then it's going to spin up faster. If you have a slower wind speed initially, it's going to spin up slower. So the time is not really constant, but the distance is constant. So lambda, the distance constant, is what we really use. So as I mentioned, for a faster wind speed, you have a shorter time to reach tau, and for a slow wind speed, you have a quicker time to reach, or a slow wind speed, you have a longer time to reach tau. So here is your equation for time constant. We are going to substitute for inertia. If you had basic physics, you probably remember the the moment of inertia for a wheel is the mass times the radius squared. So we're going to put that into that equation where you see the L on top. Actually, that's an I. We're going to put mcr squared. And when we do that, you can see that r squared and r squared cancel out, and you have mass left on top, the mass of the cup wheel. The cup wheel is basically the cup anemometer. So it's the mass, and then you have left in the bottom the velocity and also the area and the coefficient of drag and the air density. Now what we're going to do is we're going to put that tau into our equation for the distance constant, and that equation says that the distance constant is equal to tau times vi, in other words, the initial wind speed. So your tau is that all that stuff there, mc over rho c av. We'll put that into the equation. So in other words, we'll multiply tau by vi, and that gives us vi mc on top and rho c a v I in the bottom. So as you can see, the vi's cancel, and you're left with this. You're left with the distance constant, lambda, is equal to mass on top, air density in the bottom, coefficient of drag in the bottom, and the area of the cup. So this is really an important equation. It tells us that the distance constant, of course, depends upon the mass. The bigger the mass of the anemometer, the cup wheel, the longer the distance constant. And also the bigger the area of the cup, or the coefficient of drag, the shorter the distance constant. So you want a light cup wheel made of plastic instead of iron, and you want lots of coefficient of drag, and you want a big area to minimize your distance constant. So that's what this equation says. It says that if you want to minimize your distance constant, then you have to make the cup wheel light. You need to increase the size of the cups and of course decrease the mass of the cups. But for that matter, the radius of the wheel, how big that cup wheel is irrelevant, except for the mass, as it relates to the mass. So here's our new equation for the dynamic performance of a cup anemometer. So you can calculate the linear speed of the rotating cup based on the initial cup speed, the rotating speed, the initial wind speed, the step up, and then the distance constant. So the distance constants, once again, just to reiterate, is the distance that the air must travel past the anemometer for it to record 63.2% of the change in the wind speed. Typical distance constants for cup anemometers are anywhere from 1 meter to 10 meters. Of course, you want shorter distance constants because that means it spins up faster. Also, cup anemometers respond differently to a step up or step down in wind speed, and that deals with the momentum of the cup wheel. If you have a step down or the wind speed decreases, the cup tends to keep rotating longer because of its momentum. So it responds more slowly to a step down, but it responds more rapidly to a step up or an increase in wind speed. So what does this mean for a Cup Anemometer? It means that it tends to overestimate wind speeds. And the reason is if there are gusty conditions, then the wind's going up and down, and it tends to keep rotating and stay up longer than it does spin down. So Cup anemometers generally tend to overestimate the wind speed, especially in gusty conditions. So that's the dynamic performance of a Cup anemometer.